have to use the microphone?
Yes, you do.
Alice Barale.
Oh, no, you know what? Because we've got this connected. Hold on.
Hear me?
Hold on, Alice. Right now.
Hello, Alice. Can you hear us?
I can hear you. Can you hear me?
Alice Barale.
Hold on.
This is ground control.
I can hear you.
Oh, yeah. Okay, she's
Can
a
you
little
hear
low,
me?
but she can hear.
Okay, great. Great to have you. We're going to
Nice to meet you.
turn up your volume
I-
now. 1 second.
Non l'hai visto? L'ho fatto vedere.
Hello, Alice.
Hi, Sebastian. Can you hear me?
Yes, we can. This is great.
Perfect. I'm still driving because you said a little bit later, but I will be ready in 5 minutes.
Perfect. Yeah, and indeed, you know, there's no rush because we have another talk before yours. And so, yeah, we'll start your talk at 11:45.
And I'm listening to you.
Wonderful. Okay, perfect.
Thanks.
Thank you. All right, welcome back, everybody. We now start with the first real, standard session of this conference. Okay, so we really meant this as an interactive space. You know, I think we have a really mixed crowd of philosophers and machine learning, or at least people with some kind of training in philosophy or art history, and people with training in physics or machine learning. And so we really want to make the most of this mix, okay? So from now on, all the sessions will have 2 talks. One will be by a person that has more of a machine learning background. One will be of a person that has more of his background in philosophy or history of art. The important thing is that you stay as engaged as in the first part, and that you keep asking as many questions. Now after the talks, at the poster sessions, over the coffee breaks, and then I think this will be a really fun 2.5 days. So now Lorenzo is going to chair the next session.
Okay, so our next speaker will be Francesco Cagnetta from SISSA, and he will present a talk titled Towards a Theory of Generative AI, a Model-Based Approach. Thanks, Francesco.
Thank you, Lorenzo, and thanks to all the other organizers for setting this up. It's actually very exciting. And I come from a more machine learning background, and I will tell you my view of some of the focus topics of the conference. And something I want to say is that please feel free to interrupt at any point during the talk if you have any questions. All right. So just to set the stage, we are talking about generative AI, and the reason we are here all together to talk about it is that it seems to be very good at what has been trained to doing, which is to generate some content which could be novel in some sense, starting from a lot of examples used during training. And here, to give an example, I just asked ChatGPT to generate an image to represent this workshop and to generate a caption to go along with it. I'll be talking, in fact, about images and text as well. And the problem with generative AI is that we don't really understand how it works, its inner principles, and among other things, we don't understand if it can truly create new content or not. And the goal of my talk will be to understand how actually we can relate the capabilities of AI systems, in particular generative AI, to the structure of the data that have been trained on. And in this way, I hope I can convince you that we can actually quantify some of the issues that have been raised at the beginning of the workshop, in particular the combinatorial creativity of generative AI, and then maybe I'll talk a little bit about how to go even beyond this type of creativity. Okay, this is the goal. So let me first start by telling you why I think that the structure of the data matters when we talk about generative AI. And the reason is very simple. Like intuitively, if I give you these 2 images, a dog and pure noise, it looks like static on a TV. And if I ask you which one of the 2 will you select to include in the training data of whatever diffusion model, I will choose the dog. And hopefully everybody will agree. And the reason is that the dog has some structure, whereas the other image, the one on the left, has no structure at all. It's purely a noise. And the idea behind using structure is that structure is required for learning. There has to be some pattern there in the data, some rule behind the data for a model to learn it and to generate something according to this structure. So this is an intuitive explanation. There is also a more mathematical, there's actually a wealth of more mathematical explanations. But one I would like to focus on and give you a glimpse of is the cursor dimensionality. So this is this idea that the volume of a space increases very fast with the dimension of the space. So think about this little experiment. I give you some cubes, some boxes to cover some space with. And let's say that you want to cover a line, and if you need to cover a line with boxes, you might need 5 boxes, right? Now, if instead of a line, you want to cover a square on the floor, you need to use 25 boxes, 5 times 5. If you need to fill a whole room with these boxes, you need to use 125, so multiply by 5. Basically, every time you add a new dimension to your data, a new variable that your data consists of, you need to multiply the number of possibilities. And this leads to a number that quickly grows and means that unless there is some structure, the number of data you need to cover the whole of the space will be astronomical. So structure is needed. And this is the main takeaway of this discussion. Structure is crucial for learning. Therefore, having understood this, let me tell you a little bit about what are the kind of structures that people think exist behind data that can make them learnable via machine learning models. A very simple structure is the following idea, the idea that learnable tasks only depend on some features, a small number of features in the input data. And here, pictorially, I represented this with a dog that you can recognize by just doing a sketch of the contours of the face. Right? You don't need to know all of the pixels in the image to know that actually is a dog. Another idea is that there is some sort of notion of invariance of tasks for changes, right? Again, with the image of a dog as an example, I can think of the dog as being in different positions, but there's still going to be the image of a dog. Different lighting condition, orientation, different backgrounds. All of these transformations should leave the sort of concept of a dog unchanged. And this can also be used for learnability. And yet another idea, which is actually the one I'm going to focus on, is hierarchical compositionality. And this is nothing but the idea that content, whether it is images or text, are made of a collection of some high-level features. In the case of the dog, you can think of this high-level feature as the body and the background, the head of the dog. And each of these high-level features is itself composed of many lower-level features. And the reason I want to focus on this is that, well, first of all, personal interest towards this kind of structure, but also I think it's particularly interesting in the context of generative AI, because the idea of having some sort of recursive structure in which you have parts which are made of subparts, and all of these subparts can be used in different ways to create new parts, I think fits very well with the idea of possibly creating new images after having learned these basic rules. Moreover, I should say that this hierarchical compositional structure is not just found in images, but it's also found most prominently in language. And beyond language, also in music, in reasoning tasks, in mathematics, and so on. So it seems to be, let's say, a pretty good hypothesis to start from. OK. Having the hypothesis, then the research program will be how do AI or machine learning models, I should say, learn hierarchical structures. And here, by program, I really mean the sort of scientific method 101, right? I have a hypothesis on what the structure of learnable data might be, and what I need to do is to compute mathematically the implications of this hypothesis, and somehow find a way to test them in experiment. However, there is a problem, and the problem is that this hypothesis, as I formulated, is too broad. I need to be a bit more precise about what I mean with the hierarchically compositional, because this precision will lead me to a tractable model. And to introduce a tractable model, I will talk about, I will borrow actually the notion of formal grammars from linguistics. which have actually been introduced as a sort of formal tool to understand language, in particular grammatical structure. This is by now in the 50s by Chomsky. The idea is that maybe understanding a language by just listing all the possible sentences is a bit too much of a daunting task. What I can do instead is to build a generative process that creates all of the possible sentences with some rules. And this is what I'm trying to depict here. Basically, you want to generate a sentence, and the idea is that you start from a seed, a root symbol, that is the idea that you want to state a sentence. And then you have some rules, which are represented here with these branches. And is there a pointer? Yes, the branches on the tree. And these rules tell you how to expand symbols into more symbols. Basically, a sentence can be formed by a noun phrase and a verb phrase. And then I have more rules that tell me that a verb phrase can be made of a verb and an adjective, an adverb, sorry. And a noun phrase can be an adjective plus another noun phrase, or an adjective and a noun itself. And actually, this is not just been used for language. Somewhat 30 years later, some researchers have come up with method to build similar generative models for images. This is actually all pre-AI as we know it. And here, though, we're only going to think about this kind of structure as a tractable model with which we can probe the capabilities of generative AI. Basically, we're going to not understand. I'm going to give up for a little bit on the idea that I can understand how training happens on a real data set, like a collection of actual images. And I'm going to instead study the problem of learning this kind of synthetic trees. Okay, is this clear? Are there any questions so far? All right, so this is just to say that actually it's even a bit more, I have to make it even a little more simple than that. I cannot take a generic grammar. And I want to use this slide to introduce maybe a slightly technical notion of ensemble. So the idea is that I want to study really how generative machine learning models learn hierarchical structure. And to do this, I don't want to fix on the specific instances of a single data set. For instance, there might be languages that have, I don't know, the noun before the verb, or languages which have the verb before the noun. I don't want to care about this kind of structures. I only want to care about the overall hierarchical structure. And a way of doing this from physics, actually, is to consider ensembles. So I have a few structural assumptions which are fixed in terms of parameters. What are examples of this? I can fix the depth of the tree, right? I only have 3 iterations, let's say. Or I can fix what kind of symbols, the number of symbols I could have hidden in the trees, or the number of rules I can use to recombine these symbols. But this given these numbers, everything else is random, as generic as it can be. And then by studying how not a single data set is learned, but a collection of data sets sharing the same structure are learned, hopefully I can say something about the hierarchical structure. But yeah, given this, now I really want to, again, use this as a model to understand how learning happens. Therefore, I'm going to consider a pretty standard machine learning setup of having data generated like this and train neural networks in the standard generative AI paradigm, which is the one of basically giving a network a lot of examples of pristine data, and in doing so, training the network how to reconstruct corruptions of these examples. An example of this we've seen this morning by Sebastian when he described the diffusion model. There, the corruption corresponds to this addition of noise that the machines gradually learn how to remove. But other corruptions that are equally valid are the one used in language modeling, where you mask part of the sentence and then you ask the model what was missing there. And of course, first you do this by giving data where you know what the missing bit is, and then the model will eventually learn how to generate novel sentences from scratch. Okay, so everything I say from now on will apply as well to language modeling techniques or to diffusion-based techniques for images. And to quantify all of this, I'm going to always think of measuring learning curves. So learning curve is this very generic concept from, for those of you that don't know it, from cognitive science. It's just a plot, a measure of how the performance of a learner changes as the learner acquires more and more experience. And this gives you a window onto the learning process itself. So, if you actually just apply this setup I was telling you about and consider what's going to be the learning curve of this kind of hierarchical data set, what you find is this a stage-wise learning scenario, where basically what's happening is that, of course, here the measure I'm using for performance is a loss, which means that, so low loss means good performance. And as you see, it's good that, as the experience in terms of number of data that the model has seen increases, the performance improves. And there are stages in this curve. There are these little steps. And these steps correspond to nothing but the model learning a sort of deeper portion of the tree. So there are some surface level rules that are learned first. And after the surface level rules are learned, you can learn some deeper rules, and so on and so forth. In the grammar examples, let's say, this will correspond to the model first learning that maybe after a noun or before a noun, there is likely to be an article or an adjective, or close to a noun there should be a verb or something like that. Whereas higher level rules mean something like they tell you how to combine clauses, for instance, a noun phrase with a verb phrase, and so on and so forth. And okay, but yeah, really what's important to understand here is that as the machine learning model is fed more and more training data, it gradually discovers the higher level structure behind the data themselves. And I will, in the next, explore what's the implication of this in the context of generative AI. But first of all, what's important to understand about this process is that here the networks are not just learning, just memorizing sentences, so sequences of symbols, but rather they are learning the rules. And we have ways, because I've used a model, of probing whether this actually is the case or not, which is important. For instance, what does learning the rules as opposed to memorizing input combination allow you to do? It allows you to create novel combination. For instance, in this example over here, think about these two as two examples. And remember that the model only sees the bottom, the string of sequences. This is just, I put some random letters, but this could be a sentence or an image. Using this example, the model figures out that basically the combination of A and B actually has some higher level meaning I. Using this example, the model learns that higher level meaning I can be associated with the higher level meaning K. Therefore, what I can do then is to generate, having seen A, B, C, D, and D, E, F, G, if I learn the rules, I'm actually able to generate also A, B, F, G, because I know that A, B corresponds to I know that I goes next to K, and I know that K corresponds to FG. Right? That's how, by discovering rules rather than memorizing strings, you can actually generate more than you were trained on. And the first evidence for this is that you can actually understand that basically relate the several layers that the neural network has to the several layers in the generative model, and figure out that, for instance, at a very, very broad terms, the shallow layers of the network, the ones that are closer to the input, will somehow capture the low-level variables of the data, whereas the deeper layers, the ones that are further away, will capture higher-level notions, more abstract features in the data, if you will. And evidence two about this generalization phenomenon actually comes from doing some counting. So I want to compare two numbers. I want to take a sentence, fix the length of the sentence, or you could think of taking an image and fixing the size of the image as well. And I want to count first how many valid sentences of a certain length exist. And then I want to count how many training data of that length does the machine need in order to generate all of the valid sentences. And if you compare these two numbers, the first one, the number of valid sequences, is green as a function of the length of the sequence. This is an exponential explosion. Basically, the curve blows up very quickly, and if you just look at sentences of length 100, you already have 10 to the more than 100 possible sentences, which is really an astronomical number. This is like 10 with 100 zeros after. Whereas the number of training data that the machine requires in order to learn all of these sentences sits here, 10 to the 10, so much smaller than 10 to the 100. And this is an evidence that the machine has not memorized all of the possible sentences, because the data it's used is so much smaller than the total number of sentences. And I will come back to this point later, actually, because I think it has a lot of implication for combinatorial creativity. But yeah, this was the idea. It's just that the number of training data required to perform well is so much smaller than the actual number of possible sentences that exist. And what comes next, I would like to give you my view about what did we learn by looking at this model of data structure about generic data. So really think of this as a sort of an extended conclusion slide, if you will. So first of all, what I want to talk about is this notion of exponential creativity with polynomial experience, which I actually borrowed from Surya Ganguly, who's a professor at Stanford. What does it mean? It means that here really you can replace exponential with very large and polynomial with not so large. To say that models trained with a small amount of training data then have this incredible generative possibilities. And here I'm going back to the plot I showed before, but I added another line. The other line, which is the orange, has a very similar behavior as the green, if you think about it, but it's also going up much faster in the end. It reaches 10 to the 200 instead of 10 to the 100, and 200 is bigger than 100. And this, I'm basically counting, because I can, having a model, not all valid sentences, but all possible sequences of letters or of words. So even those that do not make sense, right? And this space is, of course, so much bigger than the space of sentences that actually make sense, which are the green ones. The blue, again, is the number of training data required. And I think this picture is very important in understanding really the power of generative AI, because you start from a model which has no knowledge about data at all. It's been initialized with some random weights. It could, in principle, if you ask a model to generate before training, it will generate something that looks like this, a sequence of symbols with no apparent connection with each other. But somehow, by using only this many data, so a very small amount of data, 10 to the 10, let's say, it learns that actually only 10 to the 100 of 10 to the 200 sentences are valid, which somehow summarizes the whole magic of generative model. And I think what a model like the one I studied teaches us is that there's a very easy way of enabling this combinatorial explosion of possible data by thinking about hierarchical structure. And the idea is that you have this little triangle, the rules, which are the building blocks, and you can compose rules in this fashion by stacking them on top of each other. And that's how, via composition of different rules, you allow a finite number of rules to basically create this combinatorial explosion of data. Because then when you combine them, you have to choose basically one rule per each of these triangles. So you quickly have a very large number of possibilities from a limited model. So that was, let's say, fact number 1. Another outcome, I think, of this analysis, which is interesting, is that it allows us to reveal that learning proceeds from local to global structures. And this was really the sort of hidden statement behind this picture. First, you learn close dependencies, then you learn larger dependencies, and then even larger dependencies. This is not, just applying to the synthetic data I consider, but you have similar evidences also coming from real text, where you first learn the dependencies between words that are close to each other, and then you learn dependencies between words that are far away from each other. And I want to show you a concrete example about this because I think it's pretty revealing. This is actually, it combines a bit diffusion and text because this is text generated by a diffusion model. And what I'm showing is I've trained a diffusion model with at different stages of training, so with different amount of experience, so to speak. I probe it by asking it to generate a sentence of a certain length. And as you can see, the first sentence, there is basically no correlation between the words. It makes no sense whatsoever. In popular spokesman, typeted, I don't think it's even a word. But the idea is that there is no correlations between the words. And this is mirrored here by this line, the corresponding line, which is the dark one, the black one, being flat. Now we go to the second sentence, which has been generated with the model having had a bit more experience than before. And this is the light blue curve over here. So there are some correlations, but not too many. And this is really visible because if you take two words next to each other, you can tell that the two words can be close to each other in a sentence. But then if you read the whole sentence, it doesn't make no sense again. And this means that the sort of structure that the model is learning is growing in size. Keep going even one more stage, and you get even, the sentences somehow make even more sense because you have a larger portions of the sentence that make sense altogether. Of course, you still have, these are nowhere near the scales that the actual models we were discussing, for instance, this morning are trained on. So still, as a whole, the sentence doesn't make any sense, but there is very long correlation. And this correlation, the idea is that they will keep increasing as training goes on. So from local to global. Last point, what can we say beyond combinatorial creativity? Because this was purely about hierarchical structure and having these rules that you can learn, and once you learn the rules, you can combine them to create novel inputs. And to sort of start this discussion, I want to start from this example, which is, so originally, I wanted to design this slide by having examples of what I think the average or random person I meet at any machine learning conference, maybe a year ago, would think of an imaging representing hallucination, generalization, and creativity. So this is a typical hand with 6 digits that many of you, I'm sure, have heard of. Astronaut riding a horse on the moon, and this is the initial stage of an image then eventually was modified by some digital artists and won some prize. I don't remember where. But then I was chatting with Mauro, who was in the audience yesterday, and he actually made me realize that, first of all, you should say that the definition to me seems completely off, right? If anything, this image here is the one that looks more standard in a sense, whereas this one will look a bit more innovative. And then Mauro was letting me think that actually a hand with 6 digits is much more likely to exist than a horse riding on the moon. Actually, hands with 6 digits do exist, whereas no horse can ride on the moon. So what's really are these definitions beyond the kind of, big tech-driven narrative that we heard about in the previous talk. And the idea is that can we actually use models and intuitions, such as the one I was describing before, to sort of understand and give some more precise meaning to all of these terms, and maybe possibly even debunk some notions that are there in the machine learning and general AI literature. So let's start again from the tree model. What does it mean in that case to generalize / hallucinate? Well, imagine taking a model, performing the training, and stopping at a certain level of experience, let's say here, when I've reached the second stage, but not the third. Then I ask the model to generate inputs. And because the model has only learned a limited number of rules, not all of them, the model cannot fill in too much. Right? It knows exactly how to create coherent 4-letter blocks, but then beyond that, it will just blabber. It will just generate random stuff. So before of this randomness, there is generalization. But what lies after is not clear, at least reasoning in terms of tree purely, whether to think about it as some form of hallucination, some form of just error, just something that is not what I expected it to be, or some form of novel creation. And I think that an interesting possibility is to understand this, is go beyond the hierarchical structure, which in the context of language will force us to think about semantics, not purely grammars. So this is the sentence I showed earlier. Corollars, green idea, sleep furiously. This is a sentence that's famous in the context of linguistics and formal grammars because it means nothing. It's meant to illustrate the fact that these models are very good for grammar, but do not capture semantics. Yeah, so it's a meaningless sentence. It's grammatically correct. It means nothing. And this kind of the structure that you need for forming meaningful sentences are actually called the context sensitive. So for instance, an example of this is that not all pairs of noun and verb can be allowed together, simply because not all agents are allowed the same actions. So, you know, the noun could be an animal or an inanimate object. An animate object cannot walk or cannot think, and so on. And the idea is that it's not clear when talking about this context-sensitive structure whether there are some rules that can be learned, or whether there's just we should think about them as constraints, really, that tell you, okay, I have a set of nouns and a set of verbs, and I just know that some of these nouns cannot go with some of these verbs, and I have to simply memorize all of these exceptions, all of these constraints, and so on. And it's also connected to the question of validity versus breadth in generative models. So how much I want generations to be correct, while keeping a certain breadth in terms of possibility of generating different things. And what's, I think, very interesting too about this is that if you actually, I give a talk like this, similar, in front of an audience where there were some linguists, and they told me that actually, the more you look at this sentence, which some people have had the chance to look at for like decades, the more you actually think that there is a meaning behind this sentence. An idea can definitely be green. It could be an environmental thought, and ideas can sleep. We all know about this because we have all been thinking so much in the past few years, I guess. Because I'm not pursuing that idea currently, or I just want to put it on hold while thinking about something else, right? And then what's interesting about this is that the fact that the sentence agrees with some high-level hierarchical structure, which in this case is given by the grammar, makes it even more plausible, makes somehow the hallucination here in inverted commas, because this is just an error, so to speak, from a language modeling perspective. It makes it even more plausible. And I think it's interesting because it raises the question of how much structure do you need to have learned, in a sense, in order to, by simply making a mistake, hallucinating, create something meaningful. Like an example would be, I can create, of course, I cannot train my model. That way my model can generate all possible sentences that are valid, in a sense they're made of sequences of whatever. But then typically, the sentences I will get like this will just look like nonsense. I will never judge those creative. Whereas, if I have learned already the grammar, then maybe it's possible by simple chance to generate something that some other entity, like the person training the model, will judge as a valid possibility. And with this, I think I'll stop, and I'll be happy to take questions.
Thanks, Francesco, for the very nice talk. Are there questions? Okay.
Very, very interesting talk. Do you think one can explicitly instruct a model to maybe learn the more coarse hierarchies first?
Yeah.
And would that be something that is desirable?
Courses in leave some room for low-level. Yeah, it's actually pretty hard to. So the thing is that this is. We shouldn't forget that this is analyzable using these tools like context-free grammars. But context-free grammars are a much worse model of language than a language model is. And analogously, the pattern theory, which is the approach to images, is a much worse model of images than diffusion models. So I think the bottleneck here would be knowing what the higher level structure is, as opposed to, in order to impart this knowledge on the model. Because typically you would like all these structures to be discovered by the model itself. And if you're asking, what I'm saying is that if you're not giving the structural information to the model will likely discover them from local to global, which means from low level to high level. And actually, I don't know how to, like you will need to know what the good high level variables are in order to force the model.
Like what is the reason why? Like we go from local to global?
Because there is a much, well, my hypothesis is that there is much stronger correlations between, for instance, words that are close together. You hear them much more often. And, like there are evidence for this. Even infants learning, they start from forming smaller sentences, and eventually you go to longer sentences. It's, and there's also like some actual research that shows that languages evolve in order to put together words that are more correlated. And the moment you have things that are close together that are more correlated, then you will learn from local to global.
Okay, thank you.
There was another question.
Okay, thank you. Maybe my question is too stupid. If you represent vectors in this hierarchical, like this hierarchical structure, you get rid of this exponential implosion in representation language models. So they don't, they are not exponentially big relative to the basic language, tokenized language. But if you consider training tokens, then like a new token just add it's a new adjustment of the tensor parameters. So there is no exponential implosion. So maybe I am not quite understanding what is the merit of this hierarchical structure. The model will be represented in a will be much smaller than the current models are, but I don't see where is the exponential. Where you save the exponential time where you get the polynomial time in generating the responses.
What do you mean? How can I generate exponentially many data having learned the rules, or?
No, how can you now run the model in a polynomial time? Because now where we run models, they are basically exponentially.
Well,
yeah.
if you had the model like, if you had a tree model, for the same reasons that it can be stored with not exponentially blowing up a number of parameters, it can also run in a not exponentially blowing up number of steps. Because you don't need to, because you can sort of separate generation by starting from the top. So the notion, let's say I want to generate an image of a dog, and then from that generate high-level features, and then from the high-level features, independently generate lower-level features. The hierarchical structure of generation as well allows you to also fix the problem of the time it requires to generate.
Okay.
Okay.
Thank you. That I wanted.
Other questions?
Thank you for your talk. It's really interesting to see the more mathematical, scientific side of things. I just have a question, because if I understand correctly, the more you train the model, the more the model learns, the better it gets at not hallucinating. Mm-hmm. So in a way, especially when you're using the text examples, for me that's not creativity because it doesn't make sense. And then just because it's the image, can you go back to the images that you showed, please? Like, just because there are errors in these images, does that make it creative? Because, for example, with the text, it's like, it just doesn't make sense. You're reading it, it's not even poetic from not the second example, but the first few examples that you gave. But so I'm just wondering, what would make these images actually interesting? Because if you continued training the model, it would perfect these errors. So, and I'm curious about the difference between like hallucination and just plain error. Mm-hmm. Maybe if you want to explain a little more.
Sure. Yeah, no, I think it's a valid point, and the idea is that with a purely hierarchical structure, a tree-based model, there is no distinction between hallucination and error. There is, you can generalize, you can follow the rules up to some point, and then you don't follow the rules. When you don't follow the rules, it is whatever it is, right? It could be randomly exact and still follow some other rules by chance. But this, I will say, what my claim is that is not formally different from the same phenomenon that applies to when you go beyond the training structure to this context-sensitive structure, right? Pairing a noun, such as an idea, with an incorrect verb from the point of view of context-sensitive rules, sleep, is again an error. But I think that in this case, you can already start to think of it more of, at least, as a creative choice. Right? In fact, nowadays, you can say that idea sleep. Maybe I don't know when people started to do that, but surely there was, some point in human history when it started to become frequent to have ideas and sleep put together, and before it was not the case. Yeah. And this is from a very formal, from the point of view of the definition, is the same phenomenon as the one of making mistakes in the tree generation. But because there is I think that because there is a learned hierarchical structure behind that already has fixed, for instance, the grammar, then you're more inclined to think of this as an hallucination or as an instance of creativity than the model just blubbering as in this case, right? I don't know really what's the difference between one case and the other. There's just, in both cases, there are rules that are not being followed.
And then I'm really fascinated by the image that you showed to the third one with the very sci-fi looking one on the right, because there was a lot of controversy around this image, right? And for me, I'm also questioning, why is it creative? It looks like it's something that you'd see in like Star Wars or, and especially when you consider the model is Stable Diffusion, I think that it was. Or Midjourney? Midjourney. Yeah. But either way, they're using Lion 5B, right? Like this huge database of images that are apparently the majority trained on like sci-fi or video game aesthetics. So I don't know. Everything's kind of related in that way too. When I look at this, like, is it that creative? You know what I mean? I really question that, yeah. Especially with this image in particular, a lot of images that are generated with Midjourney, they all have this kind of video game, or a lot of them have this video game or aesthetic that I think it's interesting to point out.
I entirely agree with your point. Like maybe I didn't make this this point clear enough, but really I try to think about this as like these are all example of images that I've heard being defined as creative, hallucination, generalization. These three. That's why I picked them. But I really disagree with this categorization because it, in fact, as I said, I think of the last one as the rightmost one is the least creative probably of the three of them, and then the leftmost one, which is called hallucination, is actually more likely than the middle one, which is generalization. So the point is trying to like really understand what this definition means, and can we try to give, maybe using some insights from the models I was discussing before, some more precise meaning, and really understand what we're talking about here. That's the sort of general point.
Okay, let's thank Francesco again.